Welcome everybody to this week IAMP One World Mathematical Physics Seminar. So that's the last seminar, in fact, of the year. It's a great pleasure to introduce today's speaker, Massimiliano Gubinelli from the University of Oxford. And Massimiliano will tell us about stochastic analysis of Euclidean quantum field theories, the forward-backwards equation for Grassmann measures. Massimiliano, we are looking forward to your talk.
Yeah, thank you a lot, especially to the organizer for the invitation to speak in this interesting venue. And yeah, sorry for the title, which make you speak too much, but essentially this reflects the structure of the talk, which will be in two parts. So part one, I will do some general philosophy. So if you don't like philosophy, maybe you want to come back later. And in part two, I will try to show you how this philosophy apply, or we try to apply in a particular setting of this the analysis of Grassmann measures. And so this is this is an ongoing long-term project of mine with a lot of people which joined for some parts of it or for longer parts, and especially would like to thank my group in Bonn and partly now in Oxford, which are really wonderful people, and I enjoy very much working with them. And yeah, the other are more senior collaborators, so I didn't put the photograph. You know everybody, you know the others, but somehow I think the younger colleague nicer to show. Okay, so let's go on. So this is the philosophical part. I will try to be fast because somehow, if please ask question or stop me, or we go back at the end. I just want to give you what is important to me about this project and what I'm looking for. So the problem we want to think about is this problem of studying Euclidean quantum field theory. And okay, part of the problem is that it's not clear what is this. So there are various working definition. You can say it's a probability measure on distribution, which has certain locality property and covariance properties, or you can define it via the functional integral. Let's say whatever I get at the end, it will be my quantum field theory. Practitioners know what they talk about, but somehow it's always difficult to talk with a general mathematician or geometer and try to explain to him what is really one is doing. But okay, we are in community which understands somehow at least the idea and the problem and the model. So we have a lot of example in our mind. So let's just keep to be brief, this scalar case. So I want to define a path integral, and in low dimension, I don't dare even to think about 4 dimensions. So let's say 1, 2, 3, and scalar field theory with some nonlinear interaction local. And then you know, or you could imagine there are 2 kinds of problems. So you have always this large scale problem that is, even if you were on the lattice, this measure does not have any meaning, okay? Even measure on the full lattice, you cannot write it down because it's not absolutely continuous with respect to anything. And actually, even on the lattice, you have this nice theory of Gibson specification, because mathematically, it's a very stimulating problem, how you describe this measure on the full lattice. And here you have an additional problem that you don't have a ultraviolet regulator, so you also have problem at small scale, because somehow you are bound by reflection positivity to have only certain kind of let's say gradient terms in your action. So your action has to be somehow Markovian, and this restricts the kind of interaction you can put, and regularity of the field is very low. And essentially this path integral does not live, unless you are in dimension 1, it does not live on function, but only on distribution. And this is the origin of the ultraviolet problems. That is, you cannot give a meaning to the nonlinear part, okay? And okay, I like to put books because part of the difficulty is that I try to make different community talk each other and understand the respective point of view. And this is one of the communities. I didn't know that Vincent was around, but somehow this is really the books I keep with me all the time, because yeah, here I have, yeah, one of them is here, the other one is in the back, because I try to say, they managed to do things, I want to do the same things, but we cannot yet. Okay, but this is the objective, at least reproduce results are there and maybe understand something in a way doing that. And other approaches exist actually, and they are not much mentioned in the literature as far as I know, especially in the non-perturbative case. You could try to define the measure by saying, I want to look at the measure which satisfies certain Dyson-Schwinger equation. And actually, I mentioned this because we have a recent paper with Tour and Devec. We managed somehow to understand this problem in a very particular case of the exponential interaction in two dimensions. This would not be the topic of the talk, but just to make some advertisement for this work. Yeah, this is a point of view. Grimm and Jaffe mentioned in the book, but there is, as far as I know, there is no real work in the literature. That is, can you prove that a measure which satisfies this integration by pair formula is unique, for example? Actually, even the integration by pair formula does not make sense, okay, because you have to renormalize. Here you have the interaction, and interaction has to be renormalized. This formula is to hold for any test function f. Okay, so this is for f. Okay, so or a large plus f. And then they recently start to learn about this cohomological approach, that is an integral can be defined as a cohomology class in certain algebra, cohomology of algebras, and the right language, at least in the perturbative setting, which encompasses a lot of symmetry. They know a lot about it, is Batalin-Pilkovitsky formalism, which to me it's very difficult to learn, but I'm trying. And the book of Costello and Guilliam make a link with factorization algebra, and this is a nice way to try to define what is a quantum field theory in some synthetic way, okay, without saying it's the limit of a path integral, the regularized path integral, okay. Essentially, the only method these are the methods which to define what is we are looking for. They could work even for gauge theory, so that's not a bad point of view. But I want to talk about another method. So this is stochastic quantization. This will be like the center of my interest as far as this talk is concerned. And this is actually, I looked again, is 81. Parisi-Wu and Nelson, but Nelson was looking at a different equation from a different perspective. So let me concentrate on what Parisi-Wu proposed, and was this idea that is, okay, I want to define this functional measure, and I know that at least infinitely many dimensions, I can run a dynamics, and in the equilibrium, this dynamic will converge to a stationary state, which has this measure as a marginal. And then I can compute correlation function by looking at given time. This time is a fictitious time, is a simulation time, if you want. And then these are the space-time, the Euclidean space-time are x, 1, xn. So I can look at correlation function by fixing this time and then looking at the solution to this equation, okay? So this is point of view which brings somehow in stochastic analysis. I will try to motivate. And I think, I mean, I know this equation since a long time, since essentially Iona Lazino explained it to me in 2001, maybe. And to me was the dynamic is the important part, but actually I don't think so that anymore. I think that important part is that this is a map which, given some very simple object like a Gaussian white noise, give you back a very complicated object, which is a full interacting Euclidean quantum field, okay? So I think this is the useful aspect of this map. If you concentrate on the dynamic and on the Markov property of this Markov process, is a Langevin equation, that's it's certainly true, it's all that, but more importantly is this map, which give you you give a noise, you give you back something which is an interacting object. So you give it a free theory, like Baker is out of it an interacting theory. This is important aspect, okay? So this is for me now what I like to call stochastic quantization in anything which do this. And okay, this is a lot of references. I was not very serious with reference all along the talk because it would be impossible. Only constructive quantum field theory would be pages and pages of references. But just to have an idea, since people are more familiar with constructive quantum field theory, but not with stochastic quantization, I try to lay down some landmark paper from my point of view. This is some kind of prehistory or history, whatever. But somehow, certainly, the paper of Ionel Mitter was a rigorous construction very early on in some cases, but attempt to really understand rigorously the ideas of Parisi-Wu. And then there is a book with a summary. This is very useful book which is a collection of the physics paper and everything. Then very recently I found this paper of Funaki, which was not concerned about stochastic quantization, but essentially it explained a method to estimate correlation via stochastic quantization. And then there are the Russian, Kirillov especially, and other people which in the 90s worked a lot in stochastic quantization. And I think they did really serious work, a bit impenetrable. You have really to want to find it because it's Russian. So you have to really look for the right thing because you will not find in search engine. But these two work were very interesting, especially one in Grassmann variable. We will come back later. And then integration by part formula were studied seriously by people working with the Dirichlet form. Albeverio, Röckner, Bogachev. I didn't say Bogachev has a book in finite dimension, but nobody really looked at renormalized integration by parts formula. So integration by part formula for Euclidean quantum field theory where you need a renormalization. Okay, the first work I'm aware of is on the archive since 2 weeks, and it's done by Tura and Devecchi in my group. Okay, it's not. I mean, we didn't do much, but okay, there were nothing before, as far as I'm concerned. Kirillov did something, but he didn't renormalize the measure, so he proved some limit, but it's not clear what it gets because it cannot be the right object at the end. And then the dynamics were understood by the Prato-Debussian two-dimension, and then recently there were really much energy put into understanding this problem. Eirer understood the ultraviolet renormalization in 3 dimensions for the measure, building on the structural regularity structure theory, and then Murray Weber and Albeverio Kuzuoka. And somehow we, with Olfmanova, we summarized the understanding up to that point and put all together all the elements and a paper on construction on 543. It's partial in the sense that we don't have uniqueness, but essentially any limit measure satisfies the axiom apart from the uniqueness of the vacuum and rotation, because rotation you need some uniqueness, otherwise it's difficult to preserve. And more recently, there is this very impressive work of Eirer, Chevirev, Shen, and Chandra on stochastic quantization of young meats, but for the moment, we only know the local theory. So the small field problem in constructive language, okay? The large field problem is still open. But okay, progress is steady, so until the progress stagnates, we are optimistic. So what is stochastic quantization? Yeah, sorry, I take it very far, but I like it too much to talk about it, so I cannot resist. So I always very much suggestive for me that this is a piece of a letter of Newton, and Newton discovered this very important fact for him, which was so important that he put in cryptic letters in the middle of this. So you see here. And because he didn't want to say, yeah, I tell you, but I tell you in a cryptic way so that you don't understand, because I don't want you to steal my idea, essentially. And then the idea was that you can find a global object by studying a local object and vice versa. And that, okay, you can solve differential equations and you can formulate them. And this is what I want to understand as analysis. Okay, the born of analysis is I want to understand a global geometric object by a local property, understand the local property, I can integrate and go back to the global object. Okay, so stochastic differential equation does this, but then people become more ambitious and start to look at Markov process and diffusion process. And they understood very early from Levy and others and Wiener that diffusion process cannot be very nice function. So they're a function of a different kind. The usual geometry we think about does not apply to them. And this is mathematics of the last century, but it's new mathematics. Okay, it's not classical analysis. You need some other idea to handle this kind of diffusion process, which are produced by randomness, but you don't care. Okay, you freeze the randomness, you get some picture like this, and then you want to do analysis on this picture. And of course, the idea of Newton does not go very far in this direction because you don't have a tangent there. So it's not clear how you analyze this object. And the first who understood that in a very effective way was Ito in the 40s. Okay, so it was not understood before. People were doing Markov process in the Feller way, studying the generator, studying PDEs, and never looking at the path space and the paths of the Markov process. So Ito was the first one to do it. And he did it because he wanted to understand Markov processes from the pathwise point of view. And he understood that there is a universal source of noise, which you can bend, you can bake out of it, you can make it any reasonable Markov process, okay? In a pathwise manner, okay? So this is, again, this is what I call Ito map. This is what in the literature is called Ito map. The map which you give it Brownian motion, it gives you a Markov process, for example, okay? But then it's more general. Actually, the Markov property does not enter very much into this business. And this is the stochastic analysis. And if you don't know what is stochastic analysis, you're not alone, because I don't know either, and I teach it since a lot of years, but there is no clear definition. I had to think lately, so I know what I have to teach when I teach stochastic analysis. For a long time, for me, was even probability, but I think stochastic analysis is as far as probability as probability is as far as measure theory. Because if you collapse everything, you don't see the difference, and you don't see what is important ideas. An important idea in stochastic analysis is Ito idea, is this idea here, that you can look pathwise and you can solve differential equation to go from local to global behavior. And this has nothing probabilistic, it's analysis, okay? It's not probability theory, it's stochastic analysis. And actually, I discovered recently that not alone, because Struck, in a book he wrote about stochastic analysis, he say exactly what I was thinking, and so I feel more legitimate to say, because Struck should know what is stochastic analysis. Okay, it's one of the other, and then he says that okay, there is and probabilistic and analytic ideas and techniques, and you have to understand it by way of example because there is no better definition. Okay, and if I finished my course really 2 weeks ago, and this is what I'm teaching. Ito integral, stochastic differential equation, Gaussian formula, Tanaka formula, local time. Okay, I cannot, I stop here because there is no time, but essentially this is all the things which exemplify what is today stochastic analysis, okay? Stochastic analysis is just understanding certain kind of measures, and okay, you have 2 books. So this is a book, 600 pages on Brownian motion, okay? I put the number of pages because if you go back, the book of Grimm and Jaffe is like 500 pages on more complicated objects. Okay, so this hints to the fact to me that there is still a lot to do and understand even for very simple objects. Okay, so let's see how we are at time. Yeah, I think we are in good shape. So this is summary of scheme. I'm not sure I'm very satisfied, but is the best I could come up with to try to convey you what I think about this subject. It's not mathematics, it's philosophy. So let's put things. Yeah. So Newton calculus, I would like to absorb it in this column. So you want to understand a geometric object with ellipsis of a planet orbit. Then you have a global description, which is the equation for the ellipsis. But then if you introduce a parameter, which is the speed how you go around the ellipses, then you can change the parameter a bit and you can understand what's going on locally in these ellipses, and you try to understand that locally things look like polynomials actually, and then you can write differential equation which links the local behavior to the global behavior. And Ito did the same thing for Markov processes, Markov diffusion. You have a global object, which is a Markov diffusion. It's very complicated in continuous time. In discrete time, it's trivial. Its matrix is algebra, linear algebra, with matrix, positive definite matrix. And with matrix with positive entries, actually. And in continuous time, it starts to be a craziness of madness because you have jump processes and a lot of things. And you want to construct a semi-group, and Feller point of view is that, okay, I have to solve a PDE because this semi-group solves the forward and backward PDE. But Ito point of view was, okay, you have a parameter, let's change a bit the parameter, let's see what's going on. And this semi-group change, this family of law change in a very simple matter. Locally, they change by convolution of a Gaussian. And this is all you get locally. So you have a local building block, which is a Brownian motion, which is this continuous time process, which looks Gaussian continuous. And then you have, and Ito, first object was not Ito formula. Ito formula is a byproduct of the idea. The idea is this decomposition of the Markov process and the pathwise version of it, which is easier to implement when you really do the computation. And then when you have to develop stochastic calculus to understand what is the stochastic integral here, and then you have Ito formula, okay? But Ito formula was not the original motivation of Ito, as far as I learned from the book of Struck, which met Ito and had Ito explain to him his point of view. Okay, so this is my source. And if I want to give other examples, rough path theory, it's another example of analysis, of stochastic analysis, regularity structures. You identify different building blocks and you have a way to go global to local. SLE could be, because somehow what it describes is that a growing domain in the conformally, in a random growing domain in a conformal way, and essentially tells you that the basic object is this microscopic slit which push over the domain and you can reconstruct everything with that. Anyway, so this is stochastic analysis, okay? And then I would like to propose now that this idea that you can understand stochastic quantization a la Parisi-Wu as a stochastic analysis by filling out this column, okay? What is the object is an Euclidean quantum field. Global description, yeah, here I have a semi-group. Here you have maybe the Feynman-Katz form, the path integral formulation or the Dyson-Zwinger equation, whatever you like. And then here it's more, so there is no natural parameter in this problem, at least if you don't introduce a renormalization group point of view. So, but you can introduce in various ways a parameter, and then by using this parameter, you can hope to have a global local description, and then building block usually, in the example I will show you, it's the Gaussian free field with extended with respect to this parameter. And the local to global link is played by some kind of equation, okay? In Parisi-Wu approach is the Langevin equation, which here I wrote in this form, which essentially takes the white noise or the Gaussian free field, whatever you want to call it, and produce out of it my interacting field. Okay, so this is in the sense, I think, of stochastic quantization and stochastic analysis of Euclidean quantum field. Like Ito theory, stochastic analysis of Brownian motion and all the objects you can construct over Brownian motion. In Euclidean quantum field, very likely the object is the Gaussian free field of some extension. And then in my group, then we started to play this game, or with also collaborator. Okay, let's see how many kind of stochastic analysis I can do. There is certainly the parabolic approach of Parisi-Wu, and we try to show that you can really use it to prove things, and like construction of 543 or analysis of the large field problem in 5-4 model. you can do also some kind of wave equation, because somehow you can take a more canonical point of view where you have not only the Q's, but the P also, and then you have a canonical formulation, like you have a canonical formulation of the path integral. This corresponds to a canonical formulation of the stochastic quantization, but okay. I will just mention that, okay, just to give you a panorama. I'm not talking about any of that, but this maybe I want to use this example to push away from the picture Markov property. Okay, the Markov property in my mind does not play a fundamental role in this business, because, for example, you can do an elliptic kind of stochastic quantization where there is no time. Okay, this is not a Markov process in any, there is no additional time parameter. You have a two-dimensional parameter, and actually to prove that this will give you a stochastic quantization, you have also to use some supersymmetry. So it's very, I find very nice. And yeah, and then there is also some kind of variation, optimal control formulation of the quantum field theory, which introduce some stochastic analysis. But I will talk a bit about this. So this is an optimal control problem, which gives you the partition function of your theory, and the Euler-Lagrange equation of this optimal control problem give you a forward-backward stochastic differential equation, which I will introduce later on. So this we will look in detail to this example in the case of fermions. Yeah, so this was the overview and the philosophical part. So I stop here. I think the goal for me was to try to frame what I'm telling you here in a larger context and in a larger program. And I choose this example to show how to implement this program, how we like to implement the program. And I choose it for two examples. So first, I'm not using the parabolic stochastic quantization, which is the most common one. I'm using another one, which is forward-backward SD, is essentially this last one. In the case of fermion, I don't have the variational structure, but I can write down the Euler-Lagrange equation anyway, the critical point. And then I use a Grassmann variable because I want to make a point that stochastic analysis go beyond probability theory. Okay, you can use it in non-commutative probability, and more or less it looks the same because it's not really using probabilistic concepts. It's using more idea from analysis and other things. Okay, so this is to try to remove this preconception about that stochastic quantization is about a Markov process or a Langevin equation. Is it not, in my mind? And that stochastic analysis is about probability. It is not. It's about something else, which, again, I don't know how to describe, but certainly is something else. So, okay, so this is the second part of the talk, half an hour, so I'm perfectly on schedule. We start from zero, okay? So if you didn't understood anything, that's fine. And okay, so we want to look at the Euclidean picture for fermionic particle, and essentially the first reference I know, which understand this in a clear way. Maybe Schwinger did it before, but I don't have the exact reference. But certainly for me, you can look at this paper and then they convince you that if you take fermionic theory, free fermions, let's say, and then you go into you do a weak rotation, the correlation function become correlation function, which are antisymmetric in the arguments. And therefore, there should be correlation function of fields which behave like Grassmann variable. That is, every time you exchange them, you get a minus sign. Okay, so that's the origin of this observation. As far as if you have other references, I will be happy to introduce them. So that's the idea. So essentially, the probability theory, the Euclidean quantum field for fermions are generated by Grassmann variable. And essentially what you're interested to do is to give a meaning essentially to the Feynman-Katz formula for the interaction picture of a family of fermionic field when you go in the Minkowski in the Euclidean, you get this Grassmann variable, and then you have an object which formally at least look like the bosonic one with this Beresin integral. And I prefer to write it as actually Osterwalder-Schrader do in this way. That is, you have a linear functional on the Grassmann algebra, which give you the correlation function of the free Euclidean fermions, so which satisfy very simple weak rules. So I call them Gaussian, Grassmann Gaussian. They are Grassmann variable, but they satisfy the algebraic rule of the Grassmann. And then you want to perturb this with an exponential factor. Okay, it has to be an exponential because of locality and all these other features you want to maintain, and reflection positivity and so forth. So it has the same structure and the same motivation as for the bosons. And insofar I'm concerned, this is probability theory. It's not the classical probability theory, but you have a framework to do non-commutative probability theory. So you just forget that your random variable are function on a space and that they commute as they form a commutative algebra. You take a general algebra and you impose other thing. You want a state because you want somehow to get numbers out of this, so you want linear functional on this algebra. And a nice setting, if you have a sister algebra, you can talk about norm and you can do some analysis, and then you have notion of positivity also, and you have a state. You want maybe a state which is positive, so it's continuous by definition. And now, what is a random variable in this context? It's, I learned, the first time I learned about this was in this paper. And very simply, but also very effectively, random variable is, you have to understand as an algebra of homomorphism into the algebra of random variables. Okay, so you have your algebra of interest, in our case will be a Grassmann algebra, and a random variable taking value in the Grassmann algebra, just a homomorphism which take an element in your Grassmann algebra and put it in this algebra A, which is just the algebra where you can take averages. Okay, that's very abstract, but in probability is so. Okay, in probability we teach to the student that the probability space does not have any role, because you can change probability space if you like, and that's actually very useful in many contexts. Okay, what is important are the law of the random variable and the structure which is invariant under change of probability space, actually. Okay, so this plays the role of the probability space. It's just some ground where we can put our objects, and then we put all our objects here, and we are all happy because we can do some analysis on that. Just to give you an example to understand, even in the classical setting, it's useful because if you have a random variable in a manifold, the manifold has no linear structure, so you cannot sum to random variable in a manifold, but certainly it's very well defined as a homomorphism. Okay, for any function from the manifold to the real line, you can construct a random variable, which is XF, which is just the function computed at the random point, okay, on the manifold. Okay, so as a homomorphism is well behaved and send any element of the algebra of L infinity function of bounded function on the manifold into the algebra of bounded function on my probability space. Okay, so I think this is a very effective. It's not very important for us. Okay, just I wanted to mention because we don't, even as probabilists, we never think about random variable in this way, but I think it's the most universal way to think about random variable, and it works without changes in the non-commutative setting. So in the non-commutative setting, when you want to look at Grassmann random variable, you look at them as algebra homomorphism. You give me an element of the Grassmann algebra, and they put in some way into the probability space. Different random variable put it in different ways into the probability space, so they can give different averages. Okay, this is a bit technical. We don't care about it. If you know, there is an analogy. If you know what I'm talking about, which could help you, is like a Gaussian random variable in infinite dimension does not have a canonical realization in a probability space. Okay, what you do usually is that you take a larger Banach space and then you put your random variable there. If you let's talk about Brownian motion. Okay, Brownian motion is a Gaussian process associated to the Hilbert space H1, but it does not have a realization in H1. Okay, you have to realize it in the space of continuous functions. So you have to take an arbitrary Banach space and embed H1 into this Banach space in this way. And Brownian motion takes value in the continuous function, but not in H1. Okay, so here, this is the kind of point of view I take for Grassmann variable. That is, okay, Grassmann variable a priori are objects related to a Grassmann algebra, but in order to do probability effectively, I embed in a algebra, which I don't care what it is. It has to be large enough, and you know it exists. It's proven in the appendix in some paper, and you forget about it because you don't use any of the properties. Okay. Okay, so now that we have a notion of, for example, then you can define what is a Grassmann Gaussian, and everything more or less works. I will show you something works in the standard setting, and then you have a notion of state is the state for which the field Gaussian are Gaussians, and then you want to define these formulas, and here you have the same problem we had for the bosonic case, infrared and ultraviolet. Okay, so for me, this is the same problem. It's just a bit simpler in some sense because these random variables are bounded. So they are bounded in L infinity norm, and usual Gaussian are never bounded in L infinity norm. Okay, so that's fermions are even better, as you all know better than I do. It took me some time to realize that they are not scary, but they are only better. And I breathe a lot, but now I really believe it's a very nice setting. And actually more probabilists should know them because then you can construct more objects because it's easier to construct objects there. And yeah, and this problem in many cases, actually, yeah, in many cases can be solved. And this is explained in the paper of Gavetsky, Kupiainen, Lesniewski, Rivasseau, Tenor-Magnan. All these people understood this very well. And write a lot of paper, and you can do actually a lot of things you cannot do in bosonic case, like control theory, which are asymptotically free, for example, in a rigorous way. So I think more probabilists should know because this is a really good example where you can explain a lot of features you cannot explain rigorously in other examples. And I think I understood by reading this paper of Mastro Pietro Giuliani and Richkov, which they have this point of view, which I think is very pedagogical. But of course, also the other observed that. I mean, this is clearly well known in the community, but the probabilists do not know that. They are just scared that they are not commuting, and they stop thinking about that at that point. But Ising model, you can solve it with no computing variable very easily, for example. Okay, let's talk about stochastic quantization for Grassmann measure. And the Russians were there and understood everything very early. And these papers actually, I think this is Sidor-Varavichus. This paper, actually, they really develop a nice theory. Okay, nice. Develop a theory of you want to do stochastic quantization for this variable. So you have to understand what is a Brownian motion. You have to understand how to solve a stochastic differential equation and so on and so forth. And they understood a way to do it, but somehow they were using, it's very difficult to work as they do, but because the topology is quite weak. So somehow they say something converges, all the expectation values converge, okay, which, okay, it's the natural thing, but it's very difficult to work with such a weak topology. You cannot do fixed point theorems. You cannot use anything. It's a Fréchet topology, but not a good topology on random variables. But they understood the infinite volume limit. Okay, in these papers I cite, they do stochastic quantization of a measure with the ultraviolet cutoff, but they remove the infrared cutoff. They have a mass. Okay, this is the simplest settings, but already quite impressive and interesting. And actually, I found it's so very sad that people forget about this paper because they are quite nice, actually. And then, so recently we got into this business. We wanted to do stochastic quantization, and then we adopted the point of view I explained to you with the sister algebra so that you have a norm, and there it makes things simpler. So we improved about this paper. And in this first paper, we took the infinite volume limit. But the infrared limit is more complicated. And then we took, we changed point of view. And this is what I'm going to explain, is this paper, which appeared recently in Archive. And now I try to explain to you this point of view. So let's talk about some object. You have all the standard object you need in this business. So you have a filtration of subalgebras, because these are the algebras of the random variable you know at time t. This is an increasing family of subalgebras. And then you have a conditional expectation, which projects from the larger algebra to the smaller subalgebras. And then you have a notion of Brownian motion, Grassmann Brownian motion, which has the covariance you expect to have with some twist with respect, because it has to be antisymmetric, but in time it behaves like Brownian motion. And actually, this is even better than the standard Brownian motion, okay, because it's exactly of regularity 1/2 in order. And this is the sister algebra norm. So it means from the probabilistic point of view, is an L infinity norm, okay? So this you will never have for the standard Brownian motion. You lose both in the norm and in the exponent, but here it's very nice. So it's a curve which has exactly regularity 1/2, which should be very useful for analysts, by the way, because 1/2 is always the boundary of many phenomena in this business. And then you have an Ito formula. So you can prove very easily actually an Ito formula, because you imagine now that you have a process. Now you want to do stochastic analysis. Okay, so I have Brownian motion. I have process which looks like Brownian motion, but then I could construct more complicated object by solving stochastic differential equations. And this you can do with a fixed point, and it's really quite easy. You take this Banach, this norm, and then you do your standard argument. And then this defines a process which more or less is not differentiable, because the Brownian motion has this behavior in time. So when you try to see what happens when you apply a function to this process, you get an Ito formula. We don't have yet stochastic calculus, so I cannot write a stochastic integral, but we have Ito formula in the sense of expectation. Okay, if you take an expectation, the stochastic integral disappears, and then you have somehow a martingale problem. Okay, well, if you know what it is, but essentially this is the averaged version of the Ito formula, where you have the Ito correction term, you have the derivative of the function, but the stochastic integral disappears because you took expectation with respect to an early time. So it's a martingale, it's 0. And then you have the generator of the differential equation. Okay, so if you want, here it's really like a setting of Markov processes, okay, in some Grassmann Markov processes, if you want. You have a process, and essentially the correlation, the semi-group of this process is associated to a second order differential operator, right? Exactly in the Gaussian. Okay, this is not surprise, but nobody wrote it, so we had to write it. Yeah, and okay, now this is the forward-backward SDE. So let me explain to you. So assume that you have all the standard stochastic calculus. This you have. You cannot talk about stochastic integral, but that's not used. We don't use them. Okay, stochastic integrals are difficult because they are not bounded, even for fermionic variable. Okay, so if you take a fermionic, even for Grassmann variable, the stochastic integral is only an object which is in every LP or any P, but not in L infinity. And so if you think of it as an operator, it's an unbounded operator, and we are developing some technology, but we are not there yet to end up that. But we don't care, we don't need it. So let's imagine, so you give me a function V, which you have to imagine is the potential is the interaction in your Euclidean quantum field theory, Grassmann. And then I compute its gradient. This is like the Langevin. Okay, it's not really the Langevin equation, sorry. It's a different kind of equation. So I have a parameter t. I introduce a parameter t, my problem, in the following way. I do a scale decomposition. Let's say C is the covariance of my Gaussian free field, Grassmann Gaussian free field. I introduce an ultraviolet cutoff, so I call it CT, and then I imagine that I interpolate in the parameter t between 0 and infinity. This is like you do in renormalization group. Okay, you take a scale decomposition of your covariance, and then you have a covariance which parameterized by parameter t, which is 0 is 0, and when t goes to infinity, give you the full covariance of the Gauss fermionic field. And then with this covariance, you can introduce a Gaussian martingale X by saying that the covariance of this Gaussian martingale is just C computed in the smaller of these two times. Okay, this is exactly, it's a language which seems strange, but is exactly what you do in renormalization group. You take your Gaussian free field and you decompose in scales, and then you sum up to a certain scale. So you have to imagine that xt is my Gaussian free field up to scale t, but constructed in such a way that increments are independent. Okay, so you just, okay. This is the standard construction in the renormalization group. You do it in the discrete, you can do it in the continuum, you have this Gaussian martingale in our language. So this you use a driving process to drive this stochastic differential equation, which is a very strange stochastic differential equation. It's called a forward-backward stochastic differential equation because you see at time s, the drift is determined by taking the gradient of the potential, computing on the field at a time big T. So this is the ultraviolet cutoff. Okay, T big T is the ultraviolet cutoff. Okay, so you have to have your interacting field up to the ultraviolet cutoff, then you plug inside this formula and you take average everything what happens in scale larger than scale S. Okay, so this is you condition on the path of time S. So this is forward backward because you cannot solve forward. Okay, you have to go. Essentially, you imagine you do a fixed point, you have a path, then you can compute the drift, and then you compute a new path, and then you compute the drift again. Okay, it's forward backward because you have to go up to the last time and then come back to compute the drift. But looks strange, but it's actually not very difficult to solve. Okay, just looks strange. Okay, you have computed in this way. You cannot solve it as a Cauchy problem from the starting point. Okay, because you don't know where you're arriving. So you have to solve it, for example, as a fixed point problem in the space of all path. Okay, you give me an initial path, I find a better approximation, and then you iterate, and you have a theorem which tells you that you converge. Okay, and then you have a path which is self-consistently satisfying this equation. So okay, that's one of the things that you learn when you do stochastic analysis, that actually optimization problem, for example, if you do optimal control, you have something like this. Okay, if you use Google, let me give you another example to say that it's not strange. If you use Google to go from Oxford to London, the optimal path is not computed forward, okay, it's computed backward. So Google start from London and start to compute the distance of all the places from London, and then you follow, then when you computed this quantity up your where you are, let's say Oxford, then you follow the path which is of minimal gradient, okay, in this direction. So this is exactly what you expect in an optimization problem. It's a forward-backward process. Anyway, let's define this. So why I want to define it? Because it has this marvelous property that is, this is now a new random variable. If I compute average with respect to this random variable, then it's like compute average with respect to my interacting field. Okay, this is why I was interested in that, with the cutoff, of course, and then you want to send the cutoff to infinity. Okay, so this is the slide that assumes what is a forward-backward SD. once you know, actually proving this is not very difficult. You just use the Ito formula here. It's like half-page proof when you know what you have to do. For fermions, it's even easier, actually, than for boson to prove it. But so the point is as follows. So this Gaussian martingale, it's very easy. It's a Gaussian process, so you know everything about it. You put inside this formula, you crank, you get a solution of this equation, and the solution of this equation has this property which give you the averages of the interacting field under the interacting measure. Okay, so this is a stochastic quantization in the sense I was talking about in the first part. Okay, so of course now the problem is that if you want to do it for so this works for everything. Okay, for everything in this form, and you have to have your cutoff and ultraviolet and infrared, of course. So the goal, the idea how you use this formula is, okay, I represent my correlation in this form with all my cutoff in, and then I forget about this part of the equation. I have only that at this moment, and then I just take limits in this equation. Okay, the equation is local, so taking limits is easy. For example, taking infinite volume limit, it's very easy because this equation essentially is local, so it does not care if you do infinite volume or infinite volume. Is a PDE. The PD. So what happens around the point depends on what's going on around the point. You don't see anymore the potential. The potential in infinite volume is infinite, of course, but you see the gradient of the potential, which is a local quantity. Okay. And ultraviolet problem, it's more complicated. Okay, so maybe I need, yeah, okay, I have 8 minutes as far as I see. So let's see, I try to resume what's going on. So now the problem is what you want to do to solve the ultraviolet problem, because here the ultraviolet problem will be linked to the fact that as soon as you try to send big T to infinity, everything in this formula blow up. Okay, think about you're solving some nonlinear, here you have some nonlinear interaction, your fields start to become distribution. So this is like in the bosonic case, okay? You don't have good estimate which are uniform as big T goes to infinity. So you would really like to remove big T in this picture. And your hope is that actually I don't need to see the things at the ultraviolet scale because I'm averaging everything up to some given scale S. So now you want to use why it's called backward equation? Well, because you can use it a formula on this object. You see it a function of big T and you flow back up to scale S, and then you write an Ito formula, meaning, okay, this object here, it's equal to this object here plus its derivative. And the Ito formula is what gives you the derivative. So then you have the integral between small s and big T of something. And of course, you have the derivative of the function because the function can flow. You want it to flow because you want to put it running coupling constants. You have this term, which is coming from the noise, and this is the weak contraction, okay, that you are familiar with when you integrate Gaussians. And then you have the drift term, which is like the nonlinear part, the three contribution. And then you start to see that actually here you see appearing the flow equation a la Polchinski. Okay, for the effective, this is not the effective potential, it's the effective force, because you took the gradient of the potential, but is essentially Polchinski flow equation. Okay, so if I could set this to 0, I would, so if I can solve this equation for f, I can find a function f which makes this 0, meaning if I can solve the flow equation for the renormalization group, then all this term is 0 and I'm done, okay? But of course, this is what I don't want to do, because somehow solving this equation, first of all, nobody can do it for fermions, as far as I'm concerned, not from first principles. So we cannot solve this equation. But the point is, since we have another equation, we can juggle between the two and just try to find the right balance of things which we solve in one way and things which we resolve in another way. So yeah, so I don't solve the question exactly. If you give me a function f, I compute what is here, and I cross my finger and I hope that it's small enough that I can control when t goes to infinity. Okay, so this is the approach we took. That is, we don't solve the flow equation for the renormalization group. We approximate in a well enough way, and then this is the remainder of the approximation. And then we have a price to pay, that in our equation there is a remainder, which is coming from the fact that we didn't solve the question exactly, but this remainder, it's quite nice. Okay, so we transform our original equation in a system of equation, which, however, you can opt to control when big T goes to infinity. Okay, because, for example, in the first equation, there is no big T anymore, which is the ultraviolet cutoff. In the second equation, the big T exists only as an upper integration limit. So you could hope that what you have inside the integral goes to 0 fast enough. Okay, so that's the goal. And if you use the stochastic equation, then you have this freedom that you don't have to solve the Polchinski equation right away. So this is the message of this slide, and then you can do your computation. And in the paper, actually the paper is like 40 pages, but the first 20 pages are like setup of things which we recall and which are not fun. Okay, so once you have set up the thing, since you can solve the flow equation approximately, you just solve in a finite dimensional vector space of polynomial, so that you can cancel enough term, and then you leave everything else there, and then you can set up things. You see the fields, yeah, and essentially you can handle. Let me check if I have. Yeah, so I mentioned this link with renormalization group. That is, if you are able to solve the full equation with good estimate, then you essentially you don't have to do anything else. Maybe it's worthwhile this remark, that is, to my knowledge, this is an open problem. This is controlling the fermionic Hamilton-Jacobi-Bellman equation. People tried. There is a paper of Disertori and Rivasseau which proved that somehow the tree expansion solved the Hamilton-Jacobi-Bellman equation, but somehow unless you analyze all the tree expansion, you don't see from the equation that the equation has a good solution. Okay, so being myself a PD person, I would like to take this equation and just have estimates which tell me that this equation has good solution, not have to really compute the exact solution for this equation. But yeah, so we don't do this. We approximate the solution, and then approximation is easy because you do it on a finite with finitely many polynomials. But we cannot do a critical theory yet. And yeah, okay, so so we mentioned polynomial truncation, and then you can solve. So this we used to prove that you can solve the forward-backward equation in the fold subcritical regime. Okay, so for example, we cannot handle Gros-Neveu in dimension 2. Okay, so this we cannot handle. We cannot handle Yukawa because widely enough Yukawa, as soon as you integrate the boson, looks like a Gros-Neveu more or less. So it's not easier. I don't know why, but I don't know. That's what I take from the paper of Lesniewski. But if you want, for us was exercise to see how far we could go. Okay, so thanks. This is the end of it.
Thanks, Massimiliano, for this very interesting and beautiful talk. I now leave the floor to the audience for questions or comments. So actually, I think I have one. I mean, I have a few, but let me start maybe. So I didn't quite understand. So how do you choose this auxiliary simplified dynamics? I mean, you said that's what you do, right? You approximate. There is an equation you cannot solve, then you approximate it. So can you come back on that and say a bit more about?
Yeah, it was a bit fast, but so the point is, so okay, we truncate.
So okay. This is that's a truncation on what? So what are you? I see.
Let's say you truncate the polynomials. Okay?
Yeah.
Okay. So you just allow up to certain polynomials. So you cannot, you see, at some point the nonlinear part will give you higher order polynomial, and you don't try to compare to include in the dynamics. Okay. And then the kind of bounds you get are like this. These are the kind of bound you get from renormalization group. That is the kernels you have in your effective force. They grow. They have a grow, but the more field you have, the better behavior you have. Okay. Now, what is the point? Is that the fields themselves. So you gain this factor in the kernels, but because the fields you imagine they are evaluated in a very, very low energy scale. Okay. So this is what you do in renormalization group. Now you have the high scale, you integrate, and your fields are always effective fields on a very low scale. So the fields are like constants, and then you gain this. But in the remainder, so now if you look at the remainder look like this. So this is the equation if you do the truncation. You can cancel everything, but not the higher order polynomial generated by the nonlinear part. So this higher order polynomial will have this kernel which satisfy the bound, but then they're evaluated on fields at the same scale. Okay, so you lose the gain because now the fields are not evaluated in a very low scale. So it's written here. So the fields themselves, they grow. Let's say they're distribution, so they grow. So when you evaluate the fields with the kernel at the same scale, you see from the kernel you gain beta for every field, but for every field you lose gamma. And when you are critical, near criticality, beta and gamma are equal. There are two exponents which are equal. The difference between beta and gamma is the distance from criticality, essentially. So you don't gain anything if you, so you gain but a little. So here is where we use that we are subcritical. That is, beta and gamma is slightly different. So you have a very small gain. So if you manage to have a lot of fields, then this object become integrable, and then you integrate it. Okay, so this is how you handle. So since we have subcritical, we have a very small gain, and we can use these. I mean, we can pile up. We have to keep the term into the flow equation until they're large enough and small enough, and when they're small enough, we put them there. And as soon as this object is integrable a big T, this equation, it's fine. It's very easy to solve. It's linear in R, so you get nice bound, and then you put it again here, and you solve this other equation. Of course, we can solve them only for small lambda. Okay, this is perturbative, certainly, but that's the idea. So when you are subcritical, you have at every iteration you have a finite gain in your estimates, and then you can pile up the gain and then forget from that point on. Then there is a locally, of course, there are usually, I didn't talk about it, but you have to localize to compute the renormalization constant. All these things you have to do. Okay, it's not the relevant part you handle like in the usual renormalization group is that you don't have to solve for all the equation. You truncate the equation, so it becomes very easy to solve, and then the rest goes into this remainder, and it's uniform. And this remainder compute the rest for you in some sense. Okay? Yeah.
So this, I mean, so far, I mean, this approach, you could also use it for bosons as long as you're in the small field region.
Yeah. Of course, for boson, you are never in the small field region.
Okay, but if you...
Yeah. This approach, it's the same. Actually, we used for bosons. We didn't wrote in this way because I realized later that it was the same thing, but I have a paper with Barashkov where we do 542 in the full space. We essentially did we don't use the flow equation. So 542 and 543, you don't need the flow equation in my mind because it's but for more complicated things you certainly need. And and you can use for boson, but you have to solve the small field problem. So right now this is the direction I'm working. It is in many cases, I mean, small field problem in the large field problem in the bosons, it's for 5-4 theories is I understand right now, but for other theories like St. Gordon or X model, this is more complicated. I don't understand it.
Yeah. So yeah, I just see that so there is a comment on the chat by Vincent Rivassot. So Vincent said that Disertori and himself, they defined a continuous version of renormalization group for fermions, but he thinks that so the approach of Jacques Magnin is more is closer to the initial spirit of Wilson. I don't know, Vincent, if you want to add something.
Je vais commenter en français. Je ne suis pas très bien en anglais, mais d'abord, je vais faire la référence à Schallmofer qui m'a suggéré de définir l'équation de renormalisation pour des fermions. Et en quelque sorte, Troubowitz m'a donné l'impression de mon interaction avec Troubowitz que c'était pas tellement les variables Baire, mais les variables renormalisées qui étaient importantes pour des théories effectives.
Merci, Vincent.
It's complicated. Yeah, I would agree with. Yes, I would agree with Vincent because somehow these are the interacting fields. So what I like is that these are really the interacting fields. But yeah, it's still not clear. So somehow this goes in this direction. That is, this is the like the clothed field. I don't know how to say. No, I like to think to this equation really is that this is, you see, all these theory are subcritical. No, so when you go in very or asymptotically free in the ultraviolet. So when you go in very small scale, you see the free field, which is here, and then you start to see these drift grow the interactions, let's say, with other things. And but this is the full interacting field. So somehow we see, you see in the equation, you see the effective force computed on the interacting field. I would say this goes into this direction, but it's difficult for me. Yeah, it's an open problem. So if somebody has ideas, for a long time we tried to really push up to the critical theory because I wanted to do Gros-Neveu in dimension 2. And then my collaborators start to be desperate.
Just renormalizable theory.
Yeah. But I think could be possible, but we don't see in our estimate, we don't see because you don't have, it's more complicated. So we wrote this paper just to make a point, but we are still thinking about this. Yeah.
Thanks. Other questions, comments from the audience?
Maybe just one question. You said at the moment, so you were a bit vague because of time on the conditions. Now it has become already a bit more clear in the discussion. You treat super renormalizable case for Gros-Neveu. Now at some moment you also said the infrared problem is simple, but I suspect that this means that you have some kind, at least an infrared cutoff in form of a mass, because for example two-dimensional Gros-Neveu is even more complicated in the infrared than ultraviolet. And so you say if you have an some kind of infrared regularization, it's no problem anymore or something like that.
Yeah, we have so somehow for me, of course. Let's say I'm looking at, there is a mass, and actually it has to be large with respect to the cutoff, the coupling constant. Okay, that's so for me. Let's say I'm not trying to push the result. I think we are not at the level of the kind of result you can obtain with with constructive techniques. Okay, but for me, it's more this idea that instead of describing the measure as a density with respect to another measure, this is what you do usually in statistical mechanics. Here, I want to describe the measure as the push forward. And when I say there is no problem, I'm not saying, you see, there is the mass, but there is a mass, but still, even with the mass, okay, you have to do cluster expansion, maybe, in standard theory. I mean, even on the lattice, even for Ising model, okay, the Ising model, it's easier because it's compact, but so let's say to control the correlation, you have to do cluster expansion, maybe, okay, for example.
Yeah.
And here came out in some sense in a different way, and you don't have to do cluster expansion, for example. So these are different techniques. We are trying to explore different ways to do things so that we can evaluate what are the trade-offs. The goal is not to redo things, is to try to at least have other tools, because then the goal is always the same. Okay, you want to do Young-Mills theories, you want to do theories which have geometry, you would like to do two-dimensional sigma model, and then somehow you want to understand better. This is the goal for us, to understand some technology which can be pushed, like, yeah, in this context. Okay. So yeah, it's an exploration at the moment. I think it's putting together these two worlds. Mm-hmm. But you see, people were saying to me, I think for a long time, people say to me, okay, how you control correlation? You have to do you have to do cluster expansion. And in my group, people laugh at me because they say, I don't want to anybody mention cluster expansion. Because of course you can use cluster expansion, but you don't learn anything new because you are just using the same tool. So you have to take, you have to use tie your hand a bit to try to exercise other part of your brain. And now we have a proof of decay of correlation without cluster expansion at the end of the day. It's using this idea of Funaki, which is using coupling of random variables. So this is in the spirit of stochastic analysis. You see, a proof with cluster expansion is a probabilistic proof. A proof with coupling is a stochastic analysis proof. Okay, this is the kind of difference. I'm not saying it's better, but I'm saying it's different, and maybe give a different idea, and maybe another problem where you cannot use cluster expansion, this idea you could use. But
I think maybe one can say that Vincent and Jacques, they have analyzed, if you really take the Cross-Neveu model with an ultraviolet cutoff, and then you look into these larger and larger determinants, you can also see by some kind of Taylor expansion that at some stage these determinants saturate. And so in the end, you could get convergence for a really massive theory also without doing a cluster expansion if there's an ultraviolet problem by the side. So
yeah, I studied a bit the notes of Feldman, for example.
Yeah.
They have this 1 over minus R map which integrates shells of. So it looks not very different actually. So yeah, I believe this could be possible. Yeah. Mm-hmm. But okay, let me say this works also for bosons. You see, this formalism does not really. So from the point of view of this formalism, the fact that they are fermions is just that they are bounded. Actually, we never use more than that. Mm-hmm. Mm-hmm. We don't, especially we don't write determinants.
Mm-hmm. Yeah. So thank you very much in any case for everything.
Yeah, thank you for.
Thank you. Other questions or comments?
I have a question. Can you hear me?
Yes, Malek. Go ahead.
Hey, hi Max. Yeah, I wanted to understand exactly what are the main difficulties for treating Gros-Neveu, and I mean, do you see any idea, even long shot, where?
No, I think I don't understand renormalization group well enough. So the problem is here. So you say this is what I was saying to Marcello. So what you gain? Well, if you are subcritical, what you gain, so let me remind you. So this is the scaling of the kernels. You have this decay. So this is what you gain in terms of how many fields you have in the kernels. Okay, the kernels become smaller and smaller because you generate large kernel only. They're very relevant. And the fields grow. The fields grow. So in my variable, you gain minus beta 2 to the minus beta t for any fields in the kernel, okay? And you lose 2 to the gamma t for this. This is the kind of scaling I have, okay? The fields grow and the kernel decay. So when you're critical in Gros-Neveu, you don't have this. This is beta essentially, okay? So you don't gain in this way. You gain logarithmically because the coupling constant, you gain logarithmically. So you have like factors, sorry. So in Gros-Neveu, you will have, let me try to write to you. So what I will have for Gros-Neveu, okay? You will have beta equal gamma here, for example.
Oui. Et...
And here you will have maybe some logarithmic power and something like this. Now, what is the problem? That here this beta cancel this, but you had a 3 like. So this is because it's a 4, like Gros-Neveu will be the same. So you will have like 3 gamma, 3 beta t here. So this I can never put things here because they gain only polynomially, but you have this this original divergence, which is the cube. This is the cube of the field, essentially. So it would work if at least 3 of this field here, if you have 3 fields which are very low energy, then you save other 3 of the fields and you are okay. So I think I don't understand very well how to do running. I think we are doing running coupling constant in the wrong way, but I don't understand how to do
oui,
that.
C'est pour ça que je dis que la constante de couplage, c'est la constante renormalisée, pas la constante de Baire.
Oui, oui. I'm rereading this since 3 days. Okay, I know, but I don't see it. So if you want to look, the paper, it's not long. I mean, it's really these proofs take I don't know, 10 pages. I mean, it's so if somebody has some idea, we take. I mean, we took a lot of time to think about it, and we decided to anyway have something written instead of waiting. But that's the point. Yeah, I think it should be doable, but so far I don't see how to do it. And so let me comment. There are a couple of let me do another brief comment. So now you could try. So you could try just to solve Polchinski equation. Exactly, okay, because then you don't have this problem with the remainder. And here it's curious because the problem is not given by the nonlinear term. If there were only the nonlinear term, I could solve the Polchinski equation for the fermion exactly. But the problem is given by the Laplacian term because, of course, the second derivative gives you a combinatorial factor which is too large, okay? And this is the problem, like the weak contraction, okay? And we don't see how to use Pauli principle well enough. Yeah, you don't see in the in this equation you don't see how to use Pauli principle. So you cannot beat essentially. You have the same estimate for the fermions and for the bosons, and then you are lost. Okay. So it depends how you want to approach the problem. Okay, you could say, if I was able to solve the flow equation exactly, then I would also be able to deal with the critical theory. But then I have the problem with the weak contractions. And somehow we don't see very well the Pauli principle, which you see if you do renormalization group in discrete steps, you see very well that you have better estimates for the combinatorics. That's the difference.
Thank you. Other questions or comments? Oh, it does not seem to be the case. So let's thank again Massimiliano for the very nice talk and for the very interesting discussion. Thank you.
Thank you a lot for being around and for this opportunity.